Hello, we will continue our study of sound waves by discussing a very important and common phenomenon in nature, that is resonance. Resonance occurs when objects vibrate with a frequency that is imposed on them. Every object has a natural frequency. What does that mean? If you hit any object, it will vibrate a certain number of times a second. For example, watch these beakers in here. I have 4 beakers in here. Now, each of these has a natural frequency. Listen to this. Don't they sound different? Now, if you look, these 2 beakers look alike, but I have taken some water in one of them. So the natural frequency of that is different from the natural frequency of the one without water. Now, as the size of the beaker changes, the natural frequency also changes. Now, how many of you have actually seen a choir singing with bells? Now, each bell used by each member of the choir has a natural frequency. We can actually produce all the musical notes by combining the natural frequencies of all the bells. That's a beautiful experience. All right, so every object has a natural frequency. For example, a simple pendulum of fixed length always vibrates with the same frequency. If the length of the pendulum is the same, now, for example, if this is the pendulum and you set it into vibration, it has a natural frequency. Now, that frequency will never change as long as the length remains the same. It has a natural frequency. Now, a bell, no matter how you hit it, you can hit it soft or hard, it will vibrate with the same frequency. You cannot change the frequency by the way you hit it. Now, if a swing is given a periodic push, now how many of you have experienced this? You take a child to the park and keep the child on a swing and pull the child towards you and leave. What happens? The swing goes to the other extreme and comes back. By the time it gets back, you give it a push. What happens? You need to move back because the amplitude of vibration will increase. Now, I want you to listen this carefully. I'm going to develop the concept of resonance here. Now, here the swing has a natural frequency. And I'm going to impose a force on the swing. And what is the frequency of the swing? Every time the swing completes one vibration, I give it a push. That means the frequency of the imposed force that I impose is the same as the frequency of the swing. Now, when that happens, what does the swing do? The swing will oscillate with larger and larger and larger amplitude. The amplitude of the swing will keep on increasing. That's a very interesting phenomenon. Now, every time the swing comes towards you, you give it a push. The amplitude of vibration will keep on increasing. That's right. Now, here the frequency of the external push and the natural frequency of the swing, both are the same. I hope you understand the meaning of that. The frequency, by the time the swing goes and comes back, I'm ready to give it a push. So the frequency of that push and the frequency of the swing are exactly the same. When that happens, we say the swing resonates with that external force. You see that? The swing will resonate with that external force. You understand, we even use the word resonate in our normal conversation. You say, oh yeah, what he said resonates with me. What does that mean? It means I tend to agree with it. Now here again, what happens is the natural frequency of the swing is agreeing with the frequency of the imposed force. Now what happens, instead of the imposed force being given every time the swing comes back, suppose the imposed force is given somewhere here, what will happen? The swing will stop. There is no resonance. There is no agreement. Well, resonance occurs only when the frequency of the external push is the same as the natural frequency of the swing. So I have now a definition of resonance, and I want you to understand. If a vibrating object is subjected to a periodic force with a frequency equal to the natural frequency of the object, the amplitude of vibration of the object will keep on increasing. This phenomenon is called resonance. In fact, there are very many examples in nature where resonance actually occurs. Have you ever heard of a battery of soldiers marching on a bridge and the bridge collapses in the middle? Well, what happens is the force exerted on the bridge by the marching is a periodic force. Is that right? Left, right, left. It's a periodic force. And now, if the frequency of that periodic force equal to the natural frequency of the bridge, what happens? The bridge will oscillate with greater and greater amplitude, and a stage will come when the amplitude is so great, the bridge will simply collapse. And that's the reason why, after the First World War, soldiers are not allowed to march on bridges in formation. When a battery of soldiers are to be taken across a bridge, normally their commanders ask them to disperse and walk at random. Now, have you ever heard of an opera singer shattering a glass? Well, how can an opera singer shatter a glass? Well, a glass, you know, has a natural frequency. Now, if one of the sounds produced by the opera singer is the same as the natural frequency of the glass, what will happen? The glass will vibrate with larger and larger amplitude, and a time will come when the glass cannot stand that anymore. It will simply shatter. Amazing, is that right? I remember an instant when I lived in Africa. The horn produced by a truck simply shattered the windscreen of a car. You see, this doesn't happen all the time. That happened because the natural frequency of the truck's horn was exactly equal to, the frequency of the truck's horn was exactly equal to the natural frequency of the windscreen. The windscreen oscillated with larger amplitude, which then made it shatter. All these are examples of resonances in mechanical systems. Okay. Now, the natural frequency of a stretched string is its fundamental. Now, let me take you back with the example that I have shown you very many times in the past. Now, here I have a stretched string. You have seen this. Now, this stretched string has a natural frequency. Is that right? This stretched string has a natural frequency. Now, if I impose an external force on it, I'm going to impose an external force by making this vibrate up and down. Now, if the frequency of this lip here is exactly equal to the natural frequency of the string, then the string will vibrate with larger and larger amplitude. And that's what we saw in stationary wave. Actually, stationary waves are formed when a string resonates with the frequency of an external force. You see, this is the external force. The string is going to be subjected to that. And let me show you how that happens. How that happens is, when this vibrating object vibrates, the energy of vibration is sent to the end of the string, and the energy gets reflected. By the time the reflected energy gets back, this does the next vibration. That means these two energies are now superimposed, producing a greater energy. So they agree each other. The energy of the reflected wave and the energy of the fresh vibration agree each other. They superimpose constructively. That means the string will vibrate with larger and larger amplitude. Actually, I have actually set into vibration now. There is no resonance now. You don't see a resonance. You can see the string vibrating, but there is no resonance. Why? Because the frequency of this is not equal to the natural frequency of the string. Watch what happens when I increase the frequency. There you are. Well, we have now come to a stage where the natural frequency of the string is exactly equal to the frequency of the imposed force. There you have resonance. The string now vibrates with maximum amplitude. Now, this is now 10 Hertz. Now, if the string resonates with 10 Hertz, it will also resonate with 20 Hertz. Why? Because the wave that goes and comes back, by the time it goes and comes back, there is a fresh wave created by this. There again, there is agreement. That means if the string resonates with 10 Hertz of the external force, it will resonate with 20, it will resonate with 30, it will resonate with 40, and so on. So this, you know, is the fundamental mode of vibration. So the natural frequency of a stretched string is its fundamental frequency. And now you see the fundamental frequency of the string is exactly equal to the external frequency. The string is now resonating there. I'm going to change the frequency to 20 Hertz and see what happens. Well, the string is resonating now with that 20 Hertz. You can see this is the second mode of vibration. The string is now resonating in 2 loops. Now, I increase the frequency now. You can see the resonance has disappeared. The frequency now is 22 Hertz. Now, if I want to see resonance, I must go to 30 Hertz. Alright, I'm going to go to 30. And there you see the next mode of resonance there. The string is now resonating in the third mode. The string is now resonating with the frequency 3 times its fundamental. So the string not only resonates with the frequency equal to the frequency of its fundamental, it will resonate with the frequency of twice the fundamental, 3 times the fundamental, and so on. Okay, let's move it aside. Alright, that is a good resonance there. Let me take that away. Alright, let's continue now. Well, this is what I was talking to you about, that the resonance occurs when the first wave advances and gets reflected from the pulley, and by the time the reflected wave gets back, the new wave is generated and the two will superimpose, creating the resonance. So by the time the reflected wave gets back, the second wave is ready to advance. And the energy of the second wave gets reinforced with the energy of the reflected wave, and therefore the second wave carries a greater measure of energy, and hence the amplitude will increase. Now, when this happens, the string is said to resonate with the frequency of this periodic force. So the string resonates with the frequency of the periodic force. All right, let's move on to resonance of air columns. If a string can be made to resonate with an imposed frequency, a column of air can be made to resonate with an imposed frequency. Now, how many of you have made sound with a pen cap? Now, I tell you, when I was a student, I remember many students used to disturb classes by simply blowing into their pen caps. Now here, in this pen cap, you have a column of air enclosed. Now that column of air has a natural frequency. If I can produce an external frequency which is the same as the natural frequency. Now it need not be the same as the natural frequency. It can be twice or 3 times or some multiple of the natural frequency. Is that right? If I can produce an external frequency which is some multiple of the natural frequency, then the air column inside will resonate. Resonate means it will vibrate with a large amplitude. That means you will be able to hear a loud sound. Now listen to this. I'm going to produce a frequency using my lips. Now what's happening here? One of the frequencies I produced with my lips is equal to the natural frequency of the air inside the tube, and the air therefore resonates, vibrating in large amplitude, and that created that loud sound. So a column of air enclosed in the tube has a natural frequency of vibration. This column of air can be made to resonate with the frequency of a periodic force using a tuning fork. Yes, you can do that using a tuning fork. Well, let me see if you can see this. Now, what I have done here is I want to watch whether you can actually see this. Now what I have there is a glass tube. Now what I'm going to do is remove that writing so that you can see the glass tube well. Now you have a glass tube with a column of air enclosed in it. Now this column of air inside the tube has a natural frequency. If I can vibrate a tuning fork and keep it at the mouth, and if the frequency of the tuning fork is equal to the natural frequency of the air in there, or some multiple of it, the air inside will resonate with that frequency. It will vibrate with the very large amplitude, producing a loud sound. Let's see whether the frequency of this tuning fork will resonate. Well, watch this. Well, is the frequency of the tuning fork resonating with the frequency of the air column? Well, I didn't hear a loud sound. Well, let's try another tuning fork. Well, I have another one here. Well, can you hear a sound? Well, I can hear a louder sound, but I don't think it is really resonating. There is no good agreement. There is somewhat, but not quite good. All right, let me try another one. Well, we are very nearly getting the frequency, but I don't think that is quite good enough. Let me try another one. All right? There you are. That sound is quite good, is that right? So, the air column is resonating beautifully with the frequency. The frequency of this tuning fork is 444 Hertz. That means the natural frequency of the air enclosed in it is some multiple of that. All right, listen to this one more time. The air column is resonating with the frequency of the tuning fork. All right. Now here I have drawn a picture of that. What is the specialty? Now here I have a tube just like this one, and the tube is closed at one end. Now one of the things you should know, when air column inside a tube vibrates, there will be an antinode at the mouth. You understand what an antinode is. An antinode is where the particles has maximum displacement. And at a fixed end, there will be always a node. In other words, the air particles there will not vibrate at all. So look at the mode of vibration inside a tube. There is an antinode at the mouth and a node at the closed end. So can you tell me, in your knowledge, you have the distance, the length of the tube now is the distance between an antinode and a node. How many of you remembers what is the distance between an antinode and a node in terms of the wavelength? In other words, how many waves are there? This is a stationary wave. You see, what you have inside there is a stationary wave due to resonance, just like you saw the stationary waves on the string. And so, the wavelength of a stationary wave is the distance between two alternate nodes. That means the distance between an antinode and a node is a quarter of a wavelength. Is that right? Just a quarter of a wavelength. Let me show that in here. One full wavelength is two full loops. So you got a node, and a node, an antinode, and an antinode. What we have inside the tube is an antinode and a node. So that is what we have. If this is lambda, the distance between two alternate nodes, that distance will be quarter of a lambda. So what we have inside the tube is a quarter of a lambda, distance between an antinode and a node. Well, we will be using that as we go on. Okay. Now the particles at the mouth of the tube have the maximum displacement, and particles at the fixed end will have no displacement. That will be a node. So the open end is an antinode and the closed end is a node. The higher harmonics, now this is the fundamental mode of vibration of the air inside the closed tube. Just like the string will vibrate or resonate with higher frequencies, the air enclosed in the tube will also vibrate in higher harmonics. So the higher harmonics of the air column can also be made to resonate with the frequencies of the periodic force in a similar way. So what will be the next higher mode of vibration for a tube like this? Can you think of the next higher mode? Well, let's take now two cases separately. We will consider tubes as closed tubes and open tube. Now a closed tube is something like this. A closed tube is closed at one end and open at the other end. So a closed tube is closed at one end and open at the other end. The open end will always be an antinode, and the closed end will be a node. And in the fundamental mode of vibration, a node is formed at the closed end and an antinode is formed at the mouth. So this is the fundamental mode of vibration for air inside a closed tube. Alright, what is the distance between the antinode and the node that we just talked about? Is a quarter of a lambda. So the whole length of the tube now equal to a quarter of a wavelength. The length of the tube now is a quarter of a wavelength. So we say L equal to lambda by 4. Therefore, what is lambda equal to? The wavelength of the stationary wave inside the tube now is 4L, 4 times the length of the tube. Well, what is the frequency of the fundamental? I'm going to call this time F0, the frequency of the fundamental. And if V is the speed of sound in air, can you write an equation for the frequency of the fundamental? Well, you know the wave equation, V equal to F lambda. So F equal to V over lambda. So F0, the fundamental frequency, will be V over lambda. V is the speed of sound in air, and lambda is the wavelength of the air inside the tube, and that wavelength is 4 times the length of the tube. Therefore, the frequency of the fundamental mode of vibration in a closed tube, F0 equal to V over 4L. Okay, can I ask you this? When we talked about the fundamental frequency of a stretched string, what was the equation we got? Just checking. For a stretched string, the fundamental frequency is V over 2L, because the wavelength of the wave on a stretched string for the fundamental is 2 times the length. Alright, here the wavelength is 4 times the length, therefore the fundamental frequency is V over 4L. And now, so this is the fundamental, and this is the second mode of vibration. Now look at the second mode of vibration. Now, the second mode of vibration is determined by using the understanding that the open end is always an antinode, the closed end is always a node. So, in the second mode, you have an antinode at the mouth, a node at the closed end, and an antinode and a node in between. That is the second mode of vibration in a closed tube. Can you tell me, how many wavelengths are there inside the tube? How many waves? Now, a full wave is made up of 2 full segments. And we have only 1 full segment and half of a segment there. So, since the distance between a node and an antinode is lambda by 4. So, this is a quarter lambda, this is a quarter lambda, and this is a quarter lambda. So, how many waves are there in the tube? There are 3/4 of a wavelength inside the tube. So, the length of the tube contains 3/4 of a wavelength. Alright, can you solve for lambda from here? If L equal to 3 lambda by 4, what is lambda equal to? Lambda equal to 4L over 3. Lambda equal to 4L over 3. And therefore, what is the frequency of vibration of this closed tube? F equal to V over lambda. Lambda is 4L over 3. And you see this 3 will go up it'll become 3V over 4L. But you know that V over 4L, what does V over 4L represent if you remember? V over 4L is the fundamental frequency. So in a closed tube, the second mode of vibration is 3 times the fundamental. Now what you notice here, in a closed tube, from the fundamental, the next mode is 3 times the fundamental. That means air inside a closed tube will not resonate with 2 times the fundamental. You see, that's a misfortune. Is that right? Well, that's how it happens. So for a closed tube, after the fundamental, the next mode of vibration is 3 times the fundamental. And how about the third mode of vibration? In the third mode of vibration, you have, alright, you got 2 full segments and a half segment inside the tube. So similarly, the frequency of the next mode of vibration, the frequency of this will be 5 times the fundamental. How? How many waves are there in the tube? The waves are 5 quarters, because each of this is a quarter wavelength. Therefore, the total number of wavelengths inside the tube will be 5 quarters, 5 over 4 of a wavelength. So I will be able to write like this. I have a L equal to 5 lambda over 4. Therefore, what is lambda equal to? Lambda equal to 4L over 5. Is that right? And the frequency of this mode will be V over lambda, where lambda is this. V divided by 4L over 5. And this 5 will go up. I can write it as 5 times V over 4L. But V over 4L is the fundamental frequency. So that will be 5F0. Okay. So the first mode is the fundamental. The second mode is 3 times the fundamental. That is the third harmonic. And the next one is 5 times the fundamental, the fifth harmonic. So you notice in a closed tube, all the even harmonics are missing. There is no second harmonics, no fourth harmonics, and so on. So the fundamental is the first harmonic, and the frequency of the second mode is the third harmonic. And the frequency of the third mode is the fifth harmonic. Therefore, only odd multiples of the fundamental are found in the closed tube. That means all the even harmonics are missing. So, if you want to use a tube to make a musical instrument, would you prefer a closed tube or an open tube? Well, you can answer that on your own. Let's now talk about open tube. Well, in an open tube, the mode of vibration, when the air inside an open tube vibrates, remember, at the open end, you will always have an antinode. So, because both ends are open, you have an antinode at the top, an antinode at the bottom. At both open ends, you have an antinode, and you have to have a node in the middle then. So this is the fundamental mode of vibration of an open tube. Thus the tube contains, now, how many waves are contained in the tube? Remember, the distance between an antinode and a node is a quarter of a wavelength. So here we have a quarter wavelength plus a quarter wavelength. We have half of a wavelength inside the tube. Therefore, we can say length of the tube. The length of the tube is half of a wavelength. Therefore, what is lambda equal to? Lambda is 2L. Can you now write an equation for the fundamental frequency of an open tube? What is the fundamental frequency of an open tube? Frequency F0 is V over lambda, and lambda equal to 2L, which is therefore V over 2L. You notice that the equation for the fundamental frequency of the air column in an open tube agrees with the fundamental frequency equation for the stretched string. The fundamental frequency is V over 2L. Alright, let's look at the next couple of modes. You can see that's the first harmonic, that's the second harmonic. Now in the second harmonic you have a full wave in there. So in the next mode of vibration there is a full wavelength inside the tube, and therefore lambda equal to L. The wavelength is the same as the length. You have a full wavelength inside the tube. So the frequency of this mode is therefore V over lambda, where lambda equal to L. And now I can write this as V over L is 2F0. Is that right? Okay. So the frequency of the second mode is twice the fundamental, which is the second harmonic. Similarly, the frequency of the third mode will be 3 times the fundamental, and so on. So in an open tube, you have the fundamental, you have the second harmonic, the third harmonic, the fourth harmonic, all even harmonics and odd harmonics are all present in an open tube. Okay, so we talked about open and closed tube. Let's spend a few minutes talking about musical instruments. Now, musical instruments make use of the resonant properties of materials. When an air column is set into vibration, it can resonate and produce beautiful musical notes, right? That means you can actually use columns of air to produce musical notes. But the only difference is, tell me, as I asked you, what kind of tube would you prefer? Closed tubes or open tube to produce musical notes? Well, open tubes are better because open tubes contain all harmonics. Closed tubes are missing in the odd harmonics. So in order to make a musical instrument, we would rather prefer open tube. That's right. So what is the fundamental frequency of an open tube? You have an open tube. The fundamental frequency F0 is V over 2L. And mostly what you hear in music is the fundamental frequency of the enclosed air column. And I told you the quality of a note. Along with the fundamental, you can also produce higher harmonic superimposed on it. And that's what determines the quality of the musical note. You see, a musical note that comes from a flute is different from the musical note of the same frequency that comes from a church organ. Because in addition to the fundamental frequency, which are the same for both, the higher harmonics that are superimposed on the first harmonic will be different. That makes it, or that gives that particular characteristics for the sound. So, if you use a tube, we got fundamental frequencies 1 over 2L, which means as L increases, the frequency decreases. So if you want to have a very low frequency, you have a very long tube. And as you decrease the length of the tube, the frequency will increase. You see that? So, if I keep a set of tubes like this, a very long tube then a shorter one, another shorter one, a shorter one. The frequency of vibration of air columns in here will be lower when the length is large. As the length of the tube is reduced, the frequency will increase. Now, how many of you have seen a church organ? A church organ consists of an array of these tubes. Actually, there are church organs which contains more than 1,000 tubes. Now, each tube produces a fundamental frequency of its own. So, all the musical notes, each note is produced by a tube. Okay, let's move on now. Well, all musical instruments, wind instruments, what are wind instruments? Well, a flute is a wind instrument, the church organ is a wind instrument. In other words, any instrument that uses the resonance of air columns is a wind instrument. Stringed instruments, guitar, piano, they're all stringed instruments. Percussion instrument, drum, they all use resonant vibrations of air, string, or stretched membrane. For a drum, it is a stretched membrane to produce the fundamental notes and the higher harmonics that get superimposed on it. The quality of the note produced by a given musical instrument is due to the particular combination of overtones superimposed on the fundamental frequency. Well, for some musical note, the combination of overtones are different for different instruments, giving rise to the unique quality of the note from that instrument. Well, a church organ is a wind instrument using individual pipes for musical note. We talked about that. Now, I have taken a picture of the church organ in a cathedral in Germany. In fact, this is the largest church organ in the world. If I remember, this has 1,760 tubes. There you are. That's right. St. Stephen's Cathedral in Passau, Germany. Well, my number was not correct. Has the largest church organ with 1,774 open pipes. And each of these pipes will resonate with different frequencies, producing the musical note. Alright, let me see if I can access a website. Give me a second so that we can look at some of these musical instruments. Well, it's nice to get to know some of these musical instruments. Now, on this website, you can actually study stringed instruments, wood instruments, brass, percussion, and so on. So let's look at a couple of these. Let's look at some stringed instrument. Now, this is violin. Now, how does violin sound? Let's hear that. Isn't it beautiful? How does viola sound? How does a cello sound? You can see each of these instruments produces unique sound, so that you can actually say what note comes from what instrument. Can you? If you are good in music, you will be able to say that. The frequencies may be the same, but the unique characteristics are different. Alright, how about bass? Let's look at some woodwind instrument. That's the flute. Well, how does the flute sound? Alright, how does the piccolo sound? How does the clarinet sound? And an oboe? Alright, saxophone. Bill Clinton's instrument, is that right? He used to love it, I think. Alright, let's go on and look at some brass. Well, you got the French horn. Alright, you got the trumpet. Everybody knows that. How about the tuba? Well, we got all kinds of brass in here. The trombone. Let's listen to some percussion instruments. Cymbals. How about snare drum? Well, alright, just one more drum. Okay, I think we've seen a number of musical instruments, and they're all beautiful, they're all unique, and they all have unique characteristic or timbre due to the fact that the fundamental, along with their higher harmonics, produce that unique characteristics. Alright, let's move on. Now, in the last part of our lesson, we will use the resonance tube to measure the speed of sound in air, and I need a couple of minutes to set it up, so I'm going to come back. We are now going to use the resonance of air column in a tube to measure the speed of sound in air. What we are using is a closed tube. Now, I would like you to look at this carefully because I have the apparatus in front and the shadow of this on the screen. Now, watch and see the shadow. Now, here is a glass tube. It goes all the way down, and it is connected to a reservoir, and I can put any liquid I want in it. I have some colored liquid, hoping that it will show better on the picture. Now, this is the level of the liquid. That's the level of the liquid inside the tube, which is the same as the reservoir. So what I can do is, by either raising or lowering this reservoir, I can change the level of liquid inside the tube. Now, why do I want to change the level of liquid in that tube? Because I want to change the length of the tube. You see, what I'm going to do is, I'm going to use a tuning fork and vibrate the tuning fork, keep at the mouth of the tube, and I want to find the length of the tube that will resonate with that frequency. So, what do I do? I'm going to raise this reservoir and take it somewhere here, so that you can see the level of liquid is now rising. Can you see that level rising? I hope you can. Well, at that time, what I'm going to do is, I'm going to clip this rubber tube so that I can hold that level in the tube. Okay? And I'm going to lower the reservoir. Why am I doing that? so that I can adjust the clip and allow the level to fall, and I can keep a tuning fork vibrating at the mouth. At a particular length, the fundamental mode of the air inside will resonate with the tuning fork, giving us a loud sound. Now, let's see if we can do that. I'm going to let the water fall. Well, let's see. The water level is now falling. Can you see it falling? Well, it is falling. I'm going to make it a little faster. Okay. Let's take some time to do the experiment. It's actually falling now, and I'm going to vibrate the tuning fork. Alright, let's be quiet and listen to the sound and see whether you get a resonance. Listen carefully. I don't know if the camera will pick it up. Can you hear any increased sound? All right, let's try. Did you hear? The resonance stage has passed. I'm going to stop it there. Well, it has actually gone past that length. So you actually get a resonance somewhere there. Well, the length of air in this tube, that's a closed tube, is now resonating with this frequency, 256 Hertz. Now, we can now use this to find the speed of sound. But if you are patient with, you need to be in an experiment and spend more time, you can actually get much better results on resonance. All right. Let me put this away and let's continue with our discussion. All right, got to be careful here. Put that away. All right, now I have the equipment that I have been showing you here. This is the equipment. That's the glass tube there, which is connected to a rubber tubing to a reservoir, and this reservoir can be raised or lowered to change the length of the air column there. And when the frequency of the tuning fork is equal to the natural frequency of the length of air, you have a resonance occurring. So water can be drained out of the tube slowly using a reservoir. As the length of the air column increases, the sound becomes louder, and stop the water flow when the sound has the maximum loudness. This is where the first resonance occurs. And now, measure the length of that air column. When you hear that loud sound, measure the length of that air column and let that length be L1. Alright, let's, now this is the diagram for that. Now, there is a little correction you need to apply in here, and that is, the actual antinode really does not form exactly at the mouth, but a little above it. That means a quarter wavelength is not really the length L1, but the quarter wavelength is L1 plus X. And so we would say in practice the antinode does not form exactly at the mouth of the tube, but slightly above it. Let X be the distance of the antinode from above the mouth, then L1 plus X equal to lambda by 4. Now X is called the end correction. Now what we do is, I'm not going to show this to you, the second part. Now we continue letting the water out so that you hear a second mode of vibration. Now allow the water to flow again and keep the vibrating tuning fork at the mouth of the tube. Now what happens? Stop the water flow when you hear the next loud sound. And the next loud sound will be the second mode of vibration of the closed tube. Now, what is the second mode of vibration of the closed tube? This is it. There will be 3/4 of a wave inside the tube. So, measure the length L2 at that time when you hear a loud sound for the second time. Alright? So that you get L2 plus X equal to 3 lambda by 4. And now, you got two equations, L1 plus X equal to lambda by 4, L2 plus X equal to lambda by 4, and X can be eliminated by subtracting equation 1 from equation 2. Is that equation 2 minus equation 1 is 3 lambda minus 4 minus lambda by 4. When you distribute that, x's will cancel. You get L2 minus L1 equal to lambda by 4, or lambda equal to 2 times L2 minus L1, or V equal to F lambda. F is the frequency of the tuning fork, and lambda equal to 2 times L2 minus L1. You can calculate the speed of sound as V times 2F times L2 minus L1. A nice experiment. Let's do a simple problem. An organ pipe open at both ends has a fundamental frequency of 400 Hz. If one end of this is now closed, what will be its fundamental frequency? Well, the fundamental frequency is 400 for the open pipe. Now remember, it's an open pipe. Now, what is the fundamental frequency of an open pipe? For an open pipe, F0 is V over 2L. We know V, we know F0, therefore we can find length L. So L equal to V over 2F0. Now, if F is the frequency of the tube when you close one end, the fundamental frequency, the frequency of vibration of a closed tube is F equal to V over 4L. Now that L here is V over 2F0, so replace that L by V over 2F0. What you get? V and V cancels. 2F0 will go up. It will be 2F0 divided by 4, or F0 by 2. That will be 200 Hz. Well, my tape is running out, so what I'm going to do is, I'm going to ask you, I have worked out 2 more problems for you. I want you to go and look at these problems on your own. Alright? I'm going to close this lesson with this. The shortest organ pipe used in an organs are about 7.5 centimeter. That means 0.075 meter. Therefore, the frequency of such organ pipe will be V over 2L. That is 2,267 Hz. So I've got problems like this. I'm going to leave this and I want you to go back and do some more problems. Do your homework, do the practice test, and get ready for test 1. I wish you well for test 1. Okay.